Hello again. Last time we derived the Runge-Kutta method by producing two Taylor series, one for the sort of method, which had these four constants, A through to D, and by also expanding the ordinary differential equation itself. And we compared the two series and we came up with some constraints on those constants. Today I'm just going to show you the two methods that arise from those constraints, namely the RK2 or Hoynes method and the midpoint method. And then we're going to do a worked example of the midpoint method. It's worth, after doing a fair bit of theory, to do a sort of more practical by hand example, shall we say, to see how all this works. Okay, I'll hand over the board now. Okay, so picking up where we got to last time, we derived this thing called the RK2 or Hoynes scheme. Sorry, that's not very clear, is it? Okay, middle term and my handwriting's slipping. And the idea with that is that you had these two values of your function, the function at the start of your interval, and k, and the function at the end, approximately at the end. And these were derived by comparing two Taylor series, one of the sort of method, one of the ordinary differential equation. And then a new value of x is then simply xn plus delta t on 2 k1 plus k2. So I wanted to just show two things with this. I want to show, for this specific case, the RK2 case, is a quicker way of deriving it than just doing this comparison of two Taylor series. It's almost something you realize after the fact that you've fixed all these constants, that actually there's this quicker way. But also I want to show you if k1 equals k2, which is f of x of n, we recover that xn plus 1 equals x of n plus delta t times f of x of n tn. So this is our forward Euler. So sometimes a third name for this scheme is sometimes called the modified Euler method, in the sense that if you undo all the sort of Taylor series stuff that we've done and just reset it back to this case, of course, this k1 equals k2 is a first order scheme now. We've lost the accuracy by doing that, but I just want to show you that is how it's linked in with the forward Euler. So if we take the forward Euler and we then, or you can work it the other way. So you got your forward Euler and we do another update of f in the time step, you get your RK2 scheme. So it's a modified forward Euler. So that's one observation of this scheme. And then there's a quicker derivation of RK2, and if you look around, if you do a Google search on RK2, you'll find this in the methods where they just consider this one method. If we just Taylor expand the ODE, so I'm picking up on equation 3.17 in the lecture notes that we did last time. We just do a little bit of manipulation. So that was xn plus 1 equals x of n plus delta t on f plus delta t squared on 2 plus, that's plus the order delta t cubed. Let's put it up there. But we just repartition this, so that equals x of n plus delta t on 2, and then we have so we split the f into 2 bits. We have f plus f plus delta t squared on 2 partial f by dx. And to the order of accuracy we're modeling this, then we identify that this first thing is k1, right? And the second one is k2. So k1 is simply the function of the start, and then k2 is the approximation of function within it, which is the function plus this expansion. So you could just, if you just wanted to get RK2 on its own, you could start from this point. And some exam questions I set on this sort of stuff test your understanding of whether the RK2 comes from, takes aspects of maybe the simpler derivation. Okay, so those are two observations. It's an extension of forward Euler, and there's a simpler way of deriving it. Okay, but there's the reason we have all these coefficients a, b, and c, and d is because there's another case, another type of RK scheme, and that's called the midpoint method. And if we go back to our constraints, remember we had c plus d equals 1, and dA equals dB equals a half. Okay, so another choice then is that we could choose one constant, which is c is 0. That implies that c plus d is 1 has got to be 1. And that implies that dA, dB, the A equals B equals a half. And the scheme looks like this. So you have K1 is our familiar function that starts the domain. But K2 then, whereas in the RK2 or the Hoyne scheme was trying to evaluate for f at the end of the time step, this is trying to evaluate it in the middle, hence the term midpoint. It's about approximating the function in the middle of the time step. Okay, so these two bits are the midpoint of the time step, hence the name. Okay. And then finally, we just put it all together. We have xn plus 1 equals xn plus delta t times k2. So the formula at the end just involves k2, not k2 and k1. So, I mean, another way of looking at this is that we've so just rearrange this. We've approximated dx by dt there, but what we've done, actually, let's leave that bit out. That's approximately your dx by dt bit on your left-hand side. Then you've got delta t and k2, and a k2 then is a is an approximation of your function on the right hand at the midpoint. So let's just draw a little timeline again, how it works. If that's Tn and that's Tm plus delta t, the points that you're evaluating the function on this time at the first point, and you're doing it such that you get the middle value point, and that goes into the formula. So it's structured differently from the RK2 Hoyne scheme. And these are the most common choices. I'm not actually aware of another common choice, but of course you could design your own scheme based on those constraints of C, A, B, C, and D, if you so wished. The same principle of evaluating the function multiple times is the same. So what I'm going to do is go through a worked example, actually something you could just do with a calculator if you wanted to, but easily do in MATLAB. So let's just do this. We have a worked example. And we're going to do dx by dt, and we're going to do a linear differential equation, ordinary differential equation with a known solution. 2t minus x. Now, really it's more the domain of your differential equations course to find the true solution of this. I have written out in the lecture notes how to do it with an integrating factor. What I'm going to do is actually show you the solution, and if you want to go and derive it using the integrating factor, then so I'm just going to outline the solution here, and all the steps are in the lecture notes. So we're going to use an integrating factor. So we're just trying to find the true solution first, and then we're going to then use this as a benchmark to compare the your Runge-Kutta schemes. So the idea is e to the t. So remember, I do an integrating factor, multiply both sides so you get an exact derivative, and we're going to use boundary conditions. X is 0 is -1, so the initial value of this x is -1, and then so you combine those two ingredients, you get the true solution. X star is e to the minus t, 2t minus 2. So if you're not that on top of your differential equations, just go and look at the lecture notes, and I'll go through every step of that if you're interested. I'm assuming by year 2 you should be on top of using integrating factors, but so here's the true solution. This is the true solution now. And whilst you might want to, in real applications, you might want to use Runge-Kutta for far more complicated, maybe non-linear equations, it's really good when you're testing a method to use a true solution that you know, an analytical true solution. So we do this, and then you can compare the numerical solution to the true solution directly. That's why we consider these examples. Okay, so it's not just we're just resolving an equation we can do analytically anyway. It's we're using the analytical solution as a benchmark to test the Runge-Kutta, the numerical method. Once we know that, then we can apply the Runge-Kutta method with confidence to ones that don't have analytical solutions. And going into next term, we're going to look, and the great thing about having this module over 2 terms is we can actually start to look at problems which don't have true solutions, actually require the numerics, rather than just looking at these sort of fairly sort of test cases. All right. So so the thing about this true solution is that it's when t is at t equals 1. Okay, the 2t minus 2 term goes to 0, and you have x star is e to the minus 1. So we know the true solution is e to the minus 1 at t is 1. But what about the Runge-Kutta? What solution does it get at this point? Okay. So I'm just going to show you how to do one step of this by hand, and then you can use your MATLAB or whatever to iterate. So we know that x of 0 equals -1. That's our initial conditions, and we're going to choose a time step. And what we're going to do is use the midpoint, the one we just considered. So there's the midpoint and the RK2 Hoyne scheme, the two options. But we use the midpoint in this case just for illustration, okay, so see how this method works. But writing it down by hand sometimes can help really crystallize in your mind how these schemes work. It's all to do with multiple evaluations of the function within the time step, combining them at the end, get better accuracy. That's all it is, but just doing it by hand, sort of practically, shall we say, it's helpful. So first of all, we're going to evaluate this K1, which is your function at the beginning of the time step. So that's a function at x is 0 and time is 0, right? Value at the initial bit of the time step. Okay, so remember f, the right hand side of our ODE, f is simply 2t minus x. That's your function on the right hand side. So we just plug in and x0 is minus 1. So if we plug those in, we you get f at minus 1 plus delta t on 2. Oh no, sorry. Minus 1 comma 0. If we plug in x is minus 1, t is 0, and here we just end up with 1, right? Which equals 1. So that's the easy bit, the function at the start of the domain. And then the function, so rule. So this is the function at start of time step. Got that. Function at the midpoint of the time step is approximated by K2, and K2 is f of x 0 plus K1 delta t on 2. Then delta t on 2 is the midpoint because we're starting from time as 0. We're going to 0 and minus c. Okay, let me go to the new sheet. So that means that K2 equals f of x0, which is minus 1, plus K1 times delta t on 2. K1, remember, was just 1, so it was 0.05, and the time at the midpoint, delta t on 2, was 7.05. So that's equals f at minus 0.95 or 0.05. And you plus 0.05. And you plug the numbers in, and you should end up with 1.05. Then we finish the calculation. That new value, so the new value of x, it's the old one. In terms of the midpoint rule, it's K2 times delta t. So x0, remember, was initial condition. Sorry, that's x0. Actually, I'm using notation in the lecture notes of x sub 0, which is simply x at time 0. So that is minus 1 plus K2, which we know is 1.05 times delta t, which was 0.1, which equals minus 0.895. So that might seem quite laborious, and obviously in general you code this up and you just run it. But just doing one step sometimes of a new method really sort of, as I say, hardwires into your understanding how it works. Yeah. I.e. that we understand that we're making multiple evaluations of the function and we should be returning the accuracy we want. So let's just finish that off. So we now need to, so given delta t is 0.1, right? The time step is 0.1. We want to iterate, and we want to get to a point where we're at time is 1. So we now need to iterate 10 delta t was 1 to compare with x star, the true solution at what time is 1, which was simply e to the minus 1. So I'm not going to just write out all the math steps. In fact, that's what they would have done before computers. But you can do it in MATLAB or even in a calculator if you like, but MATLAB's the most efficient. And if you want more details about how to do that, I can tell you in the live session. And that gives x at 10 is 0.3685, whereas x star at 1 is 1 over e, which numerically is 0.3678. So very close. And this is what you'll find is that it is very close, and it's only in the third decimal place does the numerical solution differ from the true solution, and this is partly because it's a second order method. But really what we need is to compare it with something lower order to see how good the so this is a midpoint. So let's now compare with the forward Euler. And you have to do this in your own time, but you can know forward Euler backwards now. You've encountered it twice. If you use the forward Euler, we get x at 10 is 0.3487. So the difference is with the forward Euler from the true solution. So this is our true solution. Let's put a box around it. This is our reference. The midpoint, because we've designed it to be second order, we know it is from the Taylor series now because we've got it through the derivation. Is much closer than the forward order. So this is second order accurate, but this is first order accurate. And with this simple example with the true solution, we can just compare the two and see actually that's what that's leading to in this case for this choice of time step is that the forward Euler is having errors or differences from the true solution in the second decimal point, whereas it's the third decimal point, the second order midpoint. Okay, it's all contingent on the size of the time step I've chosen, but in fact, a very rigorous thing to do is to actually do a multiple time steps that get smaller and smaller, and show how the midpoint method converges to the true solution, how the forward Euler, and compare it quantitatively. And you should be able to then infer by plotting it in a logarithmic plot, in fact, what the order is, and you can actually compute the convergence rate. So that's just an extension of this. So second order is a useful accuracy. Okay, and next time we've talked about second order methods. I'm going to just talk in summary about the fourth order Runge cutter, which is very useful for practical problems. The algebra is very involved, and I've decided it's beyond this sort of stage 2 course, but it's very important to be aware of Runge cutter 4. It uses exactly the same principles that we've derived already. So I'm going to stop there and stop the recording. Hello again. Last time we derived the Runge cutter method by expanding Taylor series up to second order, or order delta t cubed, and